So we basically finished 8.3 before the break. Um, on the calendar, it shows that we're going to finish 8.3 today and then start 8.4. But when I went ahead and talked about the final formula for the explicit geometric series formula. So we covered that before the break. We should be able to identify sequences as geometric or arithmetic and also write their explicit formulas using the common difference and the common ratio. What we're going to do in section 8.4 is talk about series, which is tied to sequences in that series are essentially, uh, when we have these sequences, we just have terms separated by commas. Once we start adding these terms together, so once we start putting plus, plus, plus between them, when we want to find the sum of a sequence, that's what we're going to be called. That's what's going to be called a series. And there's some notation that goes along with it, uh, mainly summation notation. Or I guess first we talk about what a series is. It's just the sum of a sequence, and then the nth partial sum specifically talks about a partial series where we're only adding one term or two terms together or three terms together or the first four terms together of a sequence. So if we said something like uh, S sub n, that would be going 3 plus 7 plus 11 plus dot 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 all the way to the nth term. Now, we need to know what the explicit formula is to be able to write this last term that we're adding in this series. So looking at this sequence, we notice that the terms are increasing by 4 every time, right? We're adding 4 every time, which means this is an arithmetic sequence. And for the arithmetic sequence, our formula for the nth term, a sub n, would be a1, which is the first term, plus d times n minus 1, right? We learned that that was the formula for an arithmetic sequence, or an explicit formula for an arithmetic sequence. So if we fill this out, the first term in the sequence is 3, the common difference is 4, and this n minus 1 signifies the location that we're at in the sequence. So this being the explicit formula for the nth term, we could just plop that right here and say we're going to add up all the way to this term here, which is the nth term, right? So you have something like a sub 1, a sub 2, a sub 3, dot, 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 and then this is a sub n. That is representing the nth term. So the sum of the first n terms, the partial nth partial sum, would be the result of this sum, whatever it is. Now, we can't really add these together unless we know what n is. So in this case, when n is 4, we're adding the first 4 terms together. When n is 3, we're adding the first 3 terms together, and so on. So that's what the nth partial sum is referring to. If we don't have a stopping point, like this, or like this, or like this, and we just put a dot, 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 and it goes on, and we add all of the terms forever in the sequence, we call that an infinite series. That means we're adding the terms of this series infinitely, or this sequence infinitely. Now, you may be thinking, well, if I just keep adding more and more numbers to this, obviously that sum is going to eventually just, well, not eventually, but that sum is going to be called infinity because this never stops and these numbers keep growing and we keep adding growing numbers together. And so the sum will end up being called infinite. But there are instances where we can add an infinite number of terms together. We can do an infinite series and calculate it and not get infinity as the result. If these numbers were getting smaller and smaller, for example, if they were approaching 0, then we may have an actual number that this infinite series is going to equal. And I think we'll get to that on Wednesday. But for now, we're more concerned with the nth partial sum situation and also this sigma notation. So let's talk about the parts of sigma notation and how to kind of go back and forth between sigma notation and just writing things out as like 3 plus 7 plus 11 plus 15, right? So there's a way to rewrite that 3, 7, 11, 15 sum in this kind of notation just to shorten our form, because while it's pretty easy to write 4 terms added together, if I wanted to write 20 terms added together, we don't really want to list 20 terms across the page. So instead, we'll use the sigma notation to signify that we're adding those 20 terms together. Okay, the parts of sigma notation. First of all, this symbol in the middle is the Greek letter sigma. That just represents the sum. So sigma represents the sum. That means we're going to add terms together. Immediately to the right of the sigma, we will have the explicit formula for the kth term of the series. So that's what I came up with here, right? I came up with it using the subscript n, but you can easily convert this to k, and then all of the n's will become k's, so you'll have an explicit formula for the kth term in the series. So this is going to be found by either recognizing that it's an arithmetic sequence and using the arithmetic sequence explicit formula, or if you have a geometric series, then we had a different formula for that one that we went over in section 8.3. You can go back and look at that if you need to refresh your memory. So the formula is going to go here. Now, if it's not arithmetic or geometric, we saw this at the beginning of chapter 8, where we kind of just looked at sequences and came up with formulas for them. In that case, you're going to look at the sequence and come up with an explicit formula for the kth term in the series. So this is just the terms of the sequence, explicit formula for the terms of the sequence. And then we have above and below the sigma, we have a starting point and a stopping point. And we always index by 1, meaning we're always going to go, we're going to count by 1 when it comes to these k's. Now, this letter doesn't have to be k on the bottom here. We can use K, we can use N, I've seen I used a lot, M used a lot. So all you need to pay attention to is that this letter matches the letter that you use in your explicit formula. And it is the starting point for your series is signified down here. This is the lower limit of summation, where this is giving you a starting number to plug into this formula. So we take this number that's down here, which doesn't have to be 1, but a lot of times sequences or series will start at 1, index 1. But if it's not, that's okay. You take this bottom number, you plug it into your explicit formula, you get the first term of your series. And then you index by 1. So if you start at 1, you plug that in, and then you go to 2, you plug that in, you go to 3, you plug that in, you go to 4, you plug that in, and then when you get to 5, that's the stopping point, which means we take 5 and we plug it in, and then we stop our series there. So notice how this example here was adding the first 4 terms of the sequence. So we would plug in 1, 2, 3, 4, and we would get these 4 terms. And then once you get all of your terms, you add them together. So let's let me do a couple of examples here. Find the terms of the series given by the explicit formula a sub k equals 2k. So our explicit formula is 2 times k. We want to start at 1 through 5. So what that means is we're going to write out the first 5 terms, essentially a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5 as the first 5 terms of this series. So formula given to us by 2 times k, where k is the subscript. So if my subscript is 1, I'm going to do 2 times 1. If the subscript is 2, I'm going to do 2 times 2, and so on. So 2 times 3, 2 times 4, 2 times 5. And we're going to evaluate these to find the terms of this series. That's 2, that's 4, 6, 8, 10. So those are the terms of the series if this is the formula and our starting index is 1 and our stopping index is 5. Now this description here, where the formula is that and we're going k equals 1 through 5, is represented down here at the bottom in sigma notation, right? When I look at this, I see, okay, we're going to add some terms together. This is the formula for finding the terms. And we're going to start at 1 and we're going to stop when we get to 5. So to evaluate this, we're going to add these terms together that we found in the previous part of this problem. So this expands into 2 plus 4 plus 6 plus 8 plus 10. Right? And when we add these together, we get 30. Right? So this sigma notation, this sum is equal to 30. Right, but the middle step there, to find these terms, you take 1, you plug it into your formula, you take 2, you plug it in the formula, 3, 4, and 5, and we stop when we plugged in the upper limit of summation. Are there any questions on the notation, the sigma notation? Okay. Here's a recap of the whole summation notation. You have your explicit formula in here, so you plug in 1, which means we're going to find a sub 1, a sub 2, all the way up to the upper limit, right? And then we're going to end up by just adding these together. Now, now that we know how this summation notation works, we should be able to take a series written out as a sum of its terms in expanded form and condense it into a summation notation form. So let's do a couple of these problems here. So as I said earlier, this lower limit doesn't have to start at 1. So if this lower limit tells you that we're starting with k equals 3, then you start with k equals 3. So if I'm going to evaluate this series given in sigma notation, I'm going to need to write out the terms to be added together. All right, so first thing we're going to do is we're going to take 3, we're going to start with 3, and plug it into our explicit formula. So my first term here will be 3 squared. Plus, and then we index by 1 and plug in the next number into the explicit formula. So after 3 comes 4, so we're going to plug in 4 into this formula, the explicit formula, so 4 squared. And so on until we've plugged in 7, right? 7 is our stopping point. So plus 5 squared plus 6 squared plus 7 squared, and we're going to stop there because 7 is our upper limit of summation. So in this case, how many terms are there in this series? There are 1, 2, 3, 4, 5 terms. All right, going from, if you count from 3 to 7, 3, 4, 5, 6, 7, you have 5 terms. And then to evaluate this, we'll just square each one of these. So that's 9 plus 16 plus 25 plus 36 plus 49. And then we will just add these together. That's 25 plus another 25 is 50. 50 plus 49 is 99 plus a 36 gives me 135. Right, and then we add them together. And so the result of an evaluation of a series like this given in sigma notation should just be a number. Should simplify to a number. All right, so you can do part B on this one. You're going to start at 2. You're going to plug in 2, plug in 3, plug in 4, plug in 5, and those are going to be the terms that you add together. All right, let's talk about how we can go from a expanded series notation into a compact sigma notation. So we want to write each series in sigma notation. And I think this one was completely done in the video, so you can check the video if you didn't already watch it to see how this one is done. I kind of want to go over a different one because doing a fraction and doing a regular sequence might be a little bit different. So let's talk about how we're going to convert this into sigma notation. Well, first of all, I can just start writing the sigma, right? I can write my sigma, and I know there's going to be 3 things to fill out here, right? We have a explicit formula that's going to go here to the right of the sigma. We need to index our variable over here on the bottom and give a starting point, give a starting number, and then put the stopping number at the top. So I'm going to use k, just because we've been using a lot of k in our notes. I'm going to leave it as k equals 1. Because if we can write this, if we can identify this as an arithmetic or geometric, we can just have k starting at 1 and use our formula for writing the explicit formula for geometric or arithmetic sequence. Looking at this, does it appear to be arithmetic or geometric? Are we adding a number every time, or are we multiplying by something every time from one term to the next?
We're multiplying.
Good. We're multiplying by 5, right? Times 5 times 5. So if you remember the arithmetic explicit formula, so explicit formula will be a sub n equals the first term times r to the n minus 1 power. Right? And if we put our first term here, that's 2 times the r, which is the common ratio, which means we're putting 5 there because we multiply by 5, and this is n minus 1. So if I wanted to find the nth term, this would be my explicit formula. All right, we plug in these numbers for A1 and R, and so this formula is what's going to get dropped into the explicit formula for our summation notation. So let's put that in there, except instead of n, we're going to use k because we used k in our summation notation indexing. So the formula we're going to put here is 2 times 5 to the k minus 1. Right? So everything else is going to be exactly the same as what we have found in our explicit formula here, except we're going to change the n to a k because that's the variable we're using for the summation notation. Now, the last part of the summation notation is the stopping point. You can't forget to stop your sequence, your series, unless this wasn't here. If this wasn't here and it said dot, dot, dot forever, then you would put infinity here, but we'll talk about that next time. Like I said, we're going to do infinite series next time. But for today, because your sequence, our sequence of sums, our sum of sequence stops, we have to tell the reader of this summation notation when to stop. What does k equal when we stop? So we need to take our explicit formula and set it equal to the stopping point, because whatever the number is up here, whether it's 7 or 8 or 10 or 11, we know that if it was 11, when we plug in 11 into this formula, we should get this last number because that's where we stop. Right? I just made up the 11. We're actually going to find what that is in a second. So how we do that is we take our explicit formula, 2 times 5 to the k minus 1, and we set it equal to our last term that we want to stop at, so that we can figure out what k is the last k that we plug in, right? We start with 1, and then when we plug in 2 for k, we should get this 10. When we plug in 3 for k, we should get this 50. When we plug in 4 for k, we should get the 250 that's coming next in the sequence, right? So when we stop is when we reach 6,250. So we're going to solve this. We're going to divide both sides by 2 to begin, which means 5 to the k minus 1 is going to equal 3,125. And how do we solve this type of, what do I do next to solve this for k? There's a couple of methods here that we can use.
Natural log.
Natural log would be one way, but if I'm in a crunch and I don't have a calculator, what's another way I can try to figure this out?
Log base 5.
Say it again.
Log base 5.
Again, would need a. I guess I wouldn't need a calculator. But before we started using logs to solve these, we used this method where we, if we have 5 to some power on the left side, if we can rewrite this 3,125 as a power of 5, which is going to take some trial and error, but we can figure out that this is a power of 5. We can rewrite it as a power of 5 to solve this. Or if you have a calculator handy, like when you're doing your homework or whatever, yes, you could just throw on a ln or log base 5 on both sides and evaluate. But for this, for this problem's sake, I'm actually going to rewrite this as 5 to the k minus 1 equals 5 to some power. Powers of 5 we can kind of jot down on the side here. 5 is 5 to the first power. Second power is 25. That times 5 is 125. That times 5 is 625. That times 5 is 3125. So it doesn't take us that far to find. So this is 5 to the first power, second, third, fourth, and fifth power. Right? So this 3,125 is 5 to the fifth. 5 to the fifth power. And then we can drop the bases, right? Because they're both base 5 on both sides. So we can now say that k minus 1 is equal to this exponent 5. This k minus 1 is equal to that exponent of 5. And so k, when we add 1, is going to be 6, which means the last number we plug into this explicit formula is 6. So we're going to put a 6 at the top of our summation notation, sigma notation. Right, so that gives us a way of going from explicit summation notation written out to sigma notation by finding the explicit formula and then figuring out what your last term is, or what index your last term is, and putting that at the top here. We did not get there. So we're going to stop there. Let me talk about something else that I think is on the worksheet. Let me look at the worksheet real quick. Right. On the worksheet, there's going to be questions where they ask you to modify these indices. So you can modify this index, the starting and the stopping index, as long as you carry that modification into your explicit formula. So if I go back to, for example, the very first example we looked at, let me draw a little box over here and work in this box. If we go back to the beginning of the section here, we had something that was k going from, what was it, the 2k, going from 1 to 5, right? It went from k equals 1 to k equals 5 of 2k. And we actually evaluated this by plugging in 1, plugging in 2, all the way to 5, and then adding them together, and we ended up getting 30, I think. Right? This was 2 plus 4 plus 6 plus 8 plus 10, and this ended up being 30. 12, 24, 30. Yeah. What we could do is we can modify the starting index so that it starts at a different point, wherever we want it to start. And all we have to do is carry that modification to all three parts of this sigma notation. So we can rewrite this sigma notation so that it starts with k equals, let's say, 0. Let's say we wanted to start our index at 0. What we could do is we can rewrite this where k starts at 0. And as long as I carry that, whatever I did, to all of the different k's, then we'll be good. What I've done from here to here is reduce the k by 1, right? Which would also reduce my stopping point by 1. So it would go from 0 to 4 as far as the indices are concerned. But we want these terms to remain the same. So if I if I reduce this k from 1 to 0, I need to kind of counteract that in my formula here. I still need to do 2 times 1 and get 2 for that first term. So remember, the first term plugged in was 1, but now the first term plugged in is going to be 0. That 0 somehow needs to turn into a 1 once I plug it in. So what you can do is you can modify this so that instead of k, we're going to put k plus 1 here. So you kind of account for that change in index by doing the opposite in your explicit formula. So if we're reducing this k from 1 to 0, then we're going to increase this one from k to k plus 1. And now if you start plugging in these k's, if I plug in 0 for k, that becomes a 0 plus 1, which is 1, times 2, which would give me a 2. And then the next index here would be plugging in 1 into here. So 1 plus 1 is 2, times 2 is 4. So we still get the same exact 2 plus 4 plus 6 plus 8 plus 10, which still gives us 30, which means these two are equal to each other in terms of their actual sum, but they look different. So these two, this and this, are equivalent series. Right? So we can change, we can mess around with the index numbering as long as we account for that in our explicit formula. And the reason why I put a parentheses here, because I just wanted to change the k from k to k plus 1, because I've reduced my index by 1. Now if I wanted to reduce by 2 or 3, then we would add 2 or 3 to this to counteract that. If we wanted to increase this index, starting index, from 1 to something higher, then we would have to do k minus that increase, right? So we have to account for that increase or decrease in the explicit formula. Okay, so you can rewrite the indices as long as you account for them in the explicit formula. All right, there's a couple of questions at the end of the worksheet that may ask you to do that, change the indices from the original numbers to new numbers. Okay, I will stop there.